The beginning before the Earth wore its familiar blue and green, before even the sun ignited its first flicker. There was only the silent dark, a cosmic hush populated by interstellar dust, rogue atoms, and the quiet, ancient memory of the very first moments of our universe. Time, as we measure it, had just begun its slow, relentless march forward. The stage was set by the collapse of earlier stars, those primordial titans who, in their death throes, scattered the elements that would one day become the building blocks of everything known and unknown: hydrogen, helium, carbon, oxygen, iron, and the trace metals that whisper through every living cell. About 4.6 billion years ago, in the unassuming suburbs of the Milky Way, a dense, cold cloud known as a molecular nebula began to collapse under its own gravity. The cause of this collapse remains a subject of scientific debate. Perhaps a supernova detonated nearby, sending shock waves to compress the cloud, or perhaps it was the inexorable slow dance of gravity itself. Within this nebula, the seeds of countless stars and worlds were sown, each destined for its own unique journey. As the nebula collapsed, it spun faster, flattening into a disk, an immense churning whirlpool of gas, dust, and ice that stretched across billions of kilometers. At the heart of this maelstrom, matter piled up, growing ever denser and hotter, until nuclear fusion ignited, the birth of our sun. Its newborn light carved away the remaining shrouds of dust, illuminating the circumstellar disk that would, grain by grain, give rise to the planets. In this protoplanetary disk, tiny grains of dust began to stick together, bound by electrostatic forces, forming clumps no larger than sand. Through millions of years, these clumps collided and merged, growing into kilometer-sized planetesimals, each a miniature world, battered and scorched by the relentless impacts of their neighbors. It was chaos and violence, a celestial melee where only the strongest survived. Among these planetesimals, in a region now known as the inner solar system, the early Earth began its long, tumultuous gestation. It was not alone. Mercury, Venus, and Mars were also coalescing from the same primordial material. But the Proto-Earth was fated to become something unique. Its mass grew, accumulating more and more material, its gravity drawing in neighbors and debris, its surface a seething ocean of molten rock. The birth of the Earth was not a singular event, but a process defined by cataclysm and transformation. Around 4.5 billion years ago, a Mars-sized body, Theia, collided with the Proto-Earth, a titanic impact that reshaped both worlds. The energy released liquefied vast swathes of the planet, ejecting molten debris into orbit. Over time, this debris coalesced to form the Moon, its pockmarked face a silent witness to those ancient days. This cataclysmic impact not only gave Earth its satellite, but also tilted its axis, set its days spinning, and perhaps even delivered essential volatiles, like water, that would become the lifeblood of the world. For hundreds of millions of years afterward, Earth remained a hostile, molten sphere, its surface battered by relentless impacts from the remnants of planetary formation. This era, known as the Hadean, was a world of fire and fury. Volcanic eruptions tore through the crust, releasing gases that would form the first toxic atmosphere, rich in carbon dioxide, methane, ammonia, and water vapor. No blue skies, no continents, no life, just a world shrouded in darkness, punctuated by the dull red glow of magma. Yet even in this inferno, the seeds of change were sown. As the planet cooled, its surface solidified into a thin, brittle crust, and torrential rains fell from the dense, steam-choked skies, filling vast basins to create the first oceans. The oldest minerals ever found, tiny zircons preserved in Western Australia, date back to about 4.4 billion years ago, and they bear silent witness to the presence of liquid water, astonishingly early in Earth's history. The formation of Earth's core, a process known as planetary differentiation, transformed the planet from the inside out. Heavier elements like iron and nickel sank to the center, forming the molten core. Lighter silicates floated outward, building the mantle and crust. The churning core generated a magnetic field, a shield invisible to the eye, but essential to life, for it would one day protect the planet from the sun's deadly solar wind, preserving the fragile atmosphere that was yet to come. All the while, the planet endured a cosmic bombardment. Between 4.1 and 3.8 billion years ago, the late heavy bombardment pelted the surface with asteroids and comets, leaving scars that would never fully heal. Some of these impacts may have delivered water and organic molecules, enriching the young oceans with the ingredients necessary for life. As the violence subsided, Earth's transformation continued. Its crust fractured into tectonic plates, setting them adrift on the slow currents of the mantle below. This restless motion, known as plate tectonics, would shape the planet's surface for eons to come, building mountains, opening rifts, and recycling continents. The earliest evidence of life appears around 3.5 to 3.8 billion years ago, in the form of ancient stromatolites, layered structures built by colonies of cyanobacteria. These simple photosynthetic organisms began to transform the atmosphere, exhaling oxygen as a byproduct of their metabolism. At first, this oxygen reacted with iron in the oceans, precipitating out as rust-red bands of ironstone. But as the supply of iron was exhausted, oxygen began to accumulate in the air, setting the stage for the rise of complex life, though this would not occur for nearly 2 more billion years. Throughout these epochs, Earth was a world in flux. Its continents wandered across the globe, driven by the relentless engine of plate tectonics. Supercontinents formed and broke apart: Rodinia, Pannotia, Gondwana, and Pangaea, each cycle reshaping the face of the planet, each breakup and collision sparking volcanic eruptions, climate shifts, and evolutionary bursts. The emergence of complex multicellular life, around 600 million years ago, was another turning point. The Cambrian explosion, 541 million years ago, unleashed a riot of forms: trilobites and anomalocarids, early vertebrates, the ancestors of all animals. Life, once confined to the oceans, began its inexorable march onto land, transforming the barren continents into lush green worlds. Through ice ages and mass extinctions, through the rise and fall of dinosaurs, the advent of flowering plants, and the slow, patient sculpting of the land by wind, water, and ice, Earth has remained a restless, dynamic world, a crucible of change. Among the many curiosities and wonders of Earth's formation, a few stand out as particularly astonishing. The moon, born of violence, stabilizes the planet's tilt, moderating the seasons and perhaps making complex life possible. The magnetic field, generated by the spinning iron core, shields the surface from solar radiation. The presence of liquid water, sustained by the greenhouse effect, and the delicate balance of atmospheric gases, is a rarity among the known planets. Even the continents themselves are strange. Earth is the only planet in the solar system with active plate tectonics, a system that recycles the crust and regulates the carbon cycle, helping to stabilize the climate over geological timescales. The oldest rocks, like the Acasta gneiss of Canada, whisper tales from nearly 4 billion years ago, while ancient Zircons hint at even earlier episodes of water and crust formation. The story of Earth's creation is not merely a tale of physics and chemistry, but a testament to the improbable, the contingent, the almost miraculous. Each step, every collision, every drop of rain, every flicker of sunlight was shaped by chance and necessity, by the blind but inexorable laws of nature, and by the whims of cosmic fortune. To stand today on the surface of this world, to breathe its air, to gaze at the moon, is to be an heir to a 4.6 billion year saga, one written in stone and water, in fire and ice, in the genes of every living thing. It is a story still unfolding, still changing, as Earth spins on beneath the ever-watchful stars. Beneath our feet, the ground tells its story in layers. In the crust, banded with the remnants of ancient volcanoes and the ashes of forgotten mountains, geologists have learned to read the Earth's autobiography, its epochs and eras marked as surely as chapters in a book. The oldest fragments, like those found in Jack Hills, Australia, are zircons, tiny, robust crystals, flecked with uranium and thorium, their isotopic ratios a clock ticking steadily backward for 4.4 billion years. These minerals, older than the oldest rocks, survived catastrophic impacts, tectonic upheavals, and the relentless grinding of time. Their chemical fingerprints reveal that Earth's surface cooled enough to support liquid water astonishingly soon after its formation, suggesting that oceans may have existed while the planet was still enduring a rain of fire from space. Much of what we know about the Earth's infancy comes not just from rocks on our planet, but from comparison to our neighbors. Mercury's lifeless cratered face, the hellish furnace of Venus, and the rust-red deserts of Mars all bear witness to different destinies. Mars may once have had oceans and rivers, but it lost its magnetic field early, and with it, its atmosphere. Venus succumbed to a runaway greenhouse effect, its surface hot enough to melt lead. Only Earth, with its delicate balance, has maintained the conditions for life over billions of years. The nature of this balance is a marvel of planetary science. The presence of the Moon, for instance, is far more than a cosmic ornament. Its gravitational pull stabilizes the tilt of Earth's axis, keeping our seasons regular. Without the Moon, the planet's tilt would wobble chaotically, as simulations by Jacques Lascar and others at the Paris Observatory showed in the 1990s. Such instability could swing climates from deep freezes to scorching summers in mere centuries, perhaps hindering the evolution of complex life. The Moon's formation, long a subject of debate, is now most widely explained by the giant impact hypothesis. Evidence comes from the similarity in isotopic ratios of oxygen and other elements in Earth and lunar rocks, samples returned by Apollo missions and analyzed in laboratories around the world. Earth's magnetic field, another guardian, is generated by the dynamo action of its rotating, convecting liquid iron core. This field deflects the solar wind, charged particles streaming from the sun at nearly 400 kilometers per second. Without this shield, the atmosphere would be stripped away, as happened on Mars. In 2015, NASA's MAVEN mission confirmed that when Mars lost its field, the solar wind rapidly eroded its once thicker atmosphere. On Earth, the magnetic field creates the auroras, painting the sky with curtains of green and red, ethereal reminders of our planet's invisible protector. One of the greatest mysteries in planetary science is the origin of Earth's water. Did it arise from within, released by volcanic outgassing? Or did it arrive from afar, delivered by comets or water-rich asteroids known as carbonaceous chondrites? Isotopic studies, notably the deuterium to hydrogen ratio in Earth's oceans compared to those in comets and meteorites, suggest a mixed origin. The debate continues, fueled by missions like ESA's Rosetta, which measured water on Comet 67P, and by the ongoing study of meteorites that have landed on Earth. Whichever the source, the presence of stable, abundant liquid water is an anomaly in the solar system, a prerequisite for life as we know it. In the Hadean and early Archean eons, Earth's surface was a dynamic canvas. The planet's internal heat, left over from formation and from radioactive decay, drove vigorous volcanism. Outgassing spewed carbon dioxide, water vapor, sulfur dioxide, ammonia, and methane into the sky, creating a thick, hot, and toxic atmosphere. Lightning danced across the clouds, and ultraviolet light from the young sun bombarded the surface. It was within this crucible, under these harsh conditions, that the first organic molecules formed, simple amino acids and nucleotides, the building blocks of life. Stanley Miller and Harold Urey, in their famous 1952 experiment at the University of Chicago, simulated these early conditions in the laboratory. By sparking a mixture of gases, they produced amino acids and other organic compounds, demonstrating that life's chemistry could arise spontaneously. But the leap from molecules to living cells remains one of the great unsolved puzzles. Did life begin in shallow pools, energized by lightning, or in the deep dark oceans near hydrothermal vents, where mineral-laden water and heat combine to create the first metabolic pathways? The discovery of ancient microfossils, isotopic signatures, and stromatolites in rocks from Greenland, South Africa, and Australia suggests that life began early, perhaps as soon as 3.8 billion years ago. These first organisms were prokaryotes, simple cells without nuclei, able to extract energy from sunlight, chemicals, or heat. Their metabolism gradually altered the atmosphere, producing oxygen as a waste product, a change that would ultimately transform the world. The Great Oxygenation Event, about 2.4 billion years ago, marked a turning point. Oxygen, initially toxic to most life, began to accumulate in the atmosphere, reacting with methane and triggering a global ice age, the first Snowball Earth. Some organisms adapted, evolving ways to use oxygen in respiration, unlocking far more energy and paving the way for complexity. The Earth's story is one of continual change, of cataclysm and renewal, of death and rebirth. The crust breaks and folds. Mountains rise and are worn away. Oceans open and close, and continents drift like rafts upon the molten mantle. The theory of plate tectonics, first proposed by Alfred Wegener in 1912, and later developed through the work of scientists like J. Tuzo Wilson, Harry Hess, and Marie Tharp, explains how these slow, inexorable movements have shaped the world. Subduction zones, where one plate dives beneath another, recycle oceanic crust and drive volcanic arcs. Rift valleys and mid-ocean ridges create new seafloor, pushing continents apart. These processes regulate the carbon cycle, drawing down carbon dioxide through weathering and burial, then releasing it through volcanic eruptions. Over millions of years, this cycle has helped maintain a stable, habitable climate, despite the increasing brightness of the sun, a phenomenon known as the faint young sun paradox. Early in Earth's history, the sun was about 30% dimmer, yet geological evidence shows liquid water was present. Greenhouse gases, likely much higher in the past, trapped enough heat to prevent the oceans from freezing, a delicate balance maintained by geological feedbacks. Life, in turn, has shaped the Earth. The rise of plants, about 470 million years ago, accelerated the drawdown of carbon dioxide, cooling the climate and allowing the spread of forests. Their roots broke up rocks, their remains formed soils, and their oxygen enriched the air. The evolution of animals, fungi, and complex ecosystems transformed the continents, creating new niches and driving waves of diversification and extinction. 5 times in the past 500 million years, life has faced near annihilation. The Permian-Triassic extinction, 252 million years ago, wiped out over 90% of marine species, likely triggered by massive volcanic eruptions, methane release, and climate chaos. The Cretaceous-Paleogene extinction, 66 million years ago, ended the reign of the dinosaurs, opening the way for mammals and, eventually, humans. The emergence of Homo sapiens, a mere 300,000 years ago, is but a blink in geological time. Yet we too are products of Earth's long story, our bones forged from ancient minerals, our brains shaped by the challenges and opportunities presented by shifting climates, changing landscapes, and the interplay of countless evolutionary forces. From the perspective of the cosmos, Earth is an anomaly, a rocky world with liquid oceans, a nitrogen-oxygen atmosphere, a magnetic field, plate tectonics, and a rich, diverse biosphere. Of the thousands of exoplanets discovered by missions like Kepler and TESS, few appear to offer such a combination of factors. The search for life beyond Earth, on Mars, on the icy moons of Jupiter and Saturn, on distant worlds orbiting other stars, is inspired by the recognition that our planet's history is both unique and universal. The Earth's story is written in code and chemistry, in the slow drift of continents and the flash of meteorites, in the whisper of genes and the roar of volcanoes. It is a story of improbable events, a collision that created the moon, a dynamo that powers the magnetic field, a balance of greenhouse gases that kept the oceans from freezing, a rise of life that transformed the air we breathe. Yet for all its scientific rigor, the tale of Earth's origin also invites wonder and reflection. What are the odds that such a world should exist? That, from the ashes of dead stars and the chaos of collisions, a planet should emerge with the capacity to nurture life, to sustain oceans and forests, to bear witness to its own story. Each step, each twist of fate, each ancient catastrophe was both inevitable and improbable, shaped by the interplay of random chance and the unyielding laws of physics. To contemplate the Earth's origin is to glimpse the vastness of time, to see our lives set against an ancient, ever-changing backdrop. The continents beneath our feet were once joined in supercontinents, then torn apart. The air we breathe was once toxic, then transformed. The sky once rained fire, then water, then snow. We are, in every sense, creatures of the Earth, our atoms born in stars, our water ancient as the rocks, our history entwined with that of the planet itself. Among the countless curiosities of Earth's formation is the mystery of its persistent habitability. The concept of the Goldilocks zone, the region around a star where liquid water can exist, explains only part of the story. Venus lies just inside, Mars just outside, yet both are inhospitable. Earth's combination of size, magnetic field, tectonics, and atmosphere is rare, perhaps even unique. Some scientists, like James Lovelock with his Gaia hypothesis, have argued that life itself helps regulate the planet, creating feedbacks that sustain habitability. While controversial, this idea underscores the profound interdependence of the biosphere and the geosphere. The story of Earth's creation continues to unfold, not only in the slow dance of continents and the evolution of life, but in human exploration and discovery. Missions like NASA's OSIRIS-REx, which returned samples from the asteroid Bennu, help us understand the materials that built the early Earth. The study of lunar rocks, meteorites, and the oldest terrestrial minerals allows us to reconstruct the events of 4.5 billion years ago. Even now, the planet changes. The continents drift, volcanoes erupt, earthquakes reshape the land. The climate warms and cools. Life adapts, evolves, and sometimes vanishes. We, as part of this living world, both witness and affect the ongoing story. To look back on Earth's origin is to see a world forged by fire and water, shaped by chance and necessity, sustained by intricate balances, and enlivened by the emergence of life. It is to understand that our home is at once ordinary, a planet among billions, and extraordinary, a cradle of consciousness, a blue world spinning in the darkness. There is poetry in the facts, and wonder in the details. The Earth's oldest minerals, the Zircons of Jack Hills, contain tiny inclusions of carbon, potential evidence, some suggest, of life more than 4 billion years ago. The oxygen in the air comes from ancient cyanobacteria, whose descendants still thrive in the world's oceans. The iron in our blood was forged in the hearts of long-dead stars, scattered in supernovae, gathered in the dust that became the Earth. The questions persist. How unique is our planet? How common are worlds like ours? What other stories are being written, even now, on distant planets orbiting distant stars? The search for exoplanets, the study of meteorites, the exploration of Mars and Europa and Enceladus, all draw on the lessons of Earth's formation. Each discovery, each new piece of data, refines our understanding and deepens the mystery. The Earth's formation was a symphony of violence and creation, a dance of dust and fire, a series of improbable events strung together by gravity and time. It was shaped by collisions, by the impact that formed the moon, by the bombardment that delivered water and organics, by the slow accretion of matter from the solar nebula. It was sculpted by internal heat and magnetic fields, by plate tectonics, and the cycles of climate and chemistry. It was transformed by life, by the rise of oxygen, by the evolution of plants and animals, by the emergence of intelligence. The story is not finished. The Earth will continue to change, to evolve, to suffer and recover from cataclysms, to nurture new forms of life and perhaps to witness the rise of new intelligences. In another 5 billion years, the sun will swell into a red giant, boiling away the oceans and consuming the inner planets. Long before then, the continents will have shifted, the atmosphere will have changed, and the world will be unrecognizable. Yet for now, we are here, on this ancient, ever-young planet. We are made of its dust, shaped by its history, sustained by its air and water. To tell the story of Earth's creation is to tell the story of ourselves, a story of wonder and complexity, of chance and necessity, of fire and water, of change and continuity. It is a story written in the stones, in the genes, in the silent testimony of ancient minerals, and in the living branches of the tree of life. It is a story that invites us to look back, to look around, and to look forward. A story that whispers of our origins and beckons us toward the future. The saga of Earth's birth and evolution is a journey through deep time, a journey that began in the darkness before the sun, that unfolded in collisions and fire, that cooled into oceans and continents, that flowered into life and consciousness. It is a journey of transformation and resilience, of destruction and renewal, of improbable beauty and enduring mystery. And so, beneath the stars, on a world billions of years in the making, the story continues.